So what can we do to the alpha carbon? We can alkylate it from either an enol or an enolate. Depending on what kind of base we use, we can form either the thermodynamic enolate, the more substituted enolate. It's the thermodynamic one because the alkene formed is more substituted, it's more stable than the kinetic enolate with the less substituted alkene that's formed in the enolate formation. But we can alkylate it in a two-step process. One, add a base. In this example at the top, we have LDA, lithium disopropylamide, and what it looks like is just the nitrogen with the two isopropyls and the negative charge on it. It's big and bulky, so it's going to pull off the hydrogen on the less substituted side. If there was a difference in cyclohexanone, obviously it's symmetrical, so it doesn't matter, but it's going to grab a hydrogen, form the enolate, and then that enolate is going to react with some alkyl halide to put a carbon bond on the alpha carbon. Okay, if it's symmetrical, it doesn't matter which side you put it on. If it's not symmetrical, unsymmetrical ketone, you have two possibilities. We have a small base that forms an equilibrium. So like ethoxide is going to go towards a thermodynamic enolate, the more substituted one. So it's going to take more energy to get over the activation energy, but it'll go down into a deeper well. Whereas the kinetic enolate, the easier to form enolate, is going to take a big, bulky, strong base that can't go back. So it's going to take less energy to get over the activation energy and fall into a higher well, basically. But those are our two choices. The thermodynamic one is more substituted, more stable. The kinetic one is less substituted and is the easier one to form. And just depends on what type of base we use. Whether it's LDA would form the kinetic enolate, partially because of the size, partially because of how strong a base it is, whereas ethoxide forms the thermodynamic enolate. So we can keep track of what can happen based on those. So if we use sodium ethoxide, we're going to add the R group onto the more substituted carbon. If we did LDA, we'd add the R group onto the less substituted carbon of an asymmetrical ketone. Now, the problem with just a plain ketone is it's not as acidic. It's harder to control what happens in everything. If we can change it to either a beta ketoester or a diester, the malonic ester synthesis, we have a lot more control over what we can do with it. So we can, with diethyl malonate, which is the structure shown at the bottom of the page here, we have two very acidic hydrogens in between the two esters. So we can have, in the first step, the ethoxide pull off the hydrogen to give us the enolate. Then we could add benzyl bromide to that and do an SN2 that comes in, kicks off the bromine to give us we could add hydroxide to that. That would cleave both of the esters to the carboxylates. So we'd go from the two ethyl esters to the two carboxylates, negatively charged oxygens because of the 8. And then from there, we could add acid and heat, and we'd protonate both of them, and we would decarboxylate to form a substituted carboxylic acid. So the malonic ester synthesis gives us a chance to alkylate onto what started out being an ester but ends up being a carboxylic acid. So we can alkylate the alpha carbon of the carboxylic acid to add on there whatever we wanted to as we needed to. And we have some more examples of this. We can put two different things on there if we use the base and some Rx. Doesn't matter what it is as long as it's a primary leaving group. We put on the red R, and then we can add base again and add the Rx. And we have to do these as 4 distinct steps, 1 through 4. It is not dump a lot of base together and dump the Rx and the red Rx and the blue Rx in there and get the product. That can't happen. You have to do it 1 step at a time to get there. And then we can cleave both of the esters to the carboxylate with the sodium hydroxide, and then add acid and heat and cleave it down to the carboxylic acid. And the decarboxylation is shown below here, where we have 2 carboxylic acids. I have them drawn so you can see in the cyclic transition state what has to happen. The carbonyl of 1 has to go grab the hydrogen, which sends the electrons down to form the double bond of CO2, and then we break the carbon-carbon bond off of that, sending off the CO2 to make the alkene, and then that can tautomerize, like we've shown before, back to the substituted carboxylic acid. Okay, and it's always this way to decarboxylate it. So if we were to show the mechanism for the tautomerization, we can have the OH send the electrons down to form the protonated acid. We got to get rid of that, which gives us the R and the H, and then all we have to do is remove the extra hydrogen, and that gets us to the carboxylic acid. And that's all that goes on in the ketoenol tautomerization. So on the next page we have the carboxylic acid shown here. How are we going to make it? So we need to think about where's the alpha carbon. That's going to be the carbon right there next to the carboxylic acid. So that's going to be the carbon that acts as the nucleophile on 2 primary leaving groups, because we have to add both of those on there. So we're going to start by drawing the molecule below and identify the alpha carbon. We'll answer the questions that it asks us to do. So we have that. Draw the molecule. So the alpha carbon, put a big purple dot there. We'll draw the molecule again and circle the groups that have to be added on to, and we'll do this in red. So this group and this group have to be added on to the alpha carbon. Now those 2 would come from having a halogen on the carbon that ends up being attached to that. So these 2 would be the alkyl halides that would be used in an SN2 in the malonic ester synthesis. And then how would we go about doing all of this? We're going to start with the diethyl malonate. We're going to add 1 ethoxide to deprotonate it, 2 benzyl bromide, then we're going to add 3 ethoxide. And remember, you have to do them stepwise. Don't add it all together. 4 the second bromide. And then 5 base. And 6 acid with a wee bit of heat. Okay? And that would get us from the diethyl malonate the first ethoxide would pull off one of the hydrogens on the alpha carbon, and then we'd add the benzyl bromide, we'd get the benzyl group on there, then we'd add the second ethoxide to pull off the second hydrogen, add the second alkyl halide, and go on from there. So in a problem like this, think about what you have to do. Think about the alpha carbon, the groups that have to attach to the alpha carbon, and what do you put on them? You have to have a leaving group on those groups because the alpha carbon is a nucleophile. And think about it the easy way, just make it a bromide or halide in general off of that carbon that has to undergo the SN2 substitution. So the other thing we can use is ethyl acetoacetate in the same sort of fashion as we did with the diethylmalonate. And with the ethyl acetoacetate, we can pull off a hydrogen with ethoxide, add the benzyl bromide, and then add the benzyl bromide, and then we add the base to form the carboxylate. And then from there, we add acid and heat, and we decarboxylate it, and we get the ketone, the substituted ketone, as opposed to in the previous example with the diethylmalonate, we got the substituted carboxylic acid. Here we get the substituted ketone. Same sort of process. The decarboxylation is much the same in that we have a ketone and a carboxylic acid. It's the carbonyl shown up above that takes the hydrogen off of the carboxylic acid, forming the CO2, forming the enol as that leaves, and then we tautomerize that to get the substituted ketone. Okay, it's the same sort of thing. So we can do this with two things, and as we said before, we have to separate it out 1, 2, 3, and 4 to put on one R group. That's reactions 1 and 2, and then 3 and 4, the second R group. They can't be all combined together. We have to do them one at a time, and then we cleave the ester to the carboxylate, and then acid and heat, and we get the substituted ketone. Here we've put two groups on it, so we have two groups added on. It's the same sort of process as we had before. So what has to happen here, we're going to draw the molecule showing the alpha carbon. So here the alpha carbon is the purple dot. Draw the molecule where we circle the groups that have to be added on to the alpha carbon. We'll circle them in red. So it's these two. Okay, let's erase the longer line there and cut a little wild with my bond. And then draw the necessary alkyl halides. It's going to be the same as above, the benzyl bromide, and then the bromine on the off of the 5-membered ring. Now, what chemical reaction would we do? We would start with ethyl acetoacetate. We would add ethoxide. We would add a benzyl bromide, phenyl CH2Br. Don't lose the CH2, it's important. Then we would add more ethoxide. Then we would add the other CH2 with our cyclopentane. And then we would add hydroxide to cleave the ester to the carboxylate, and then acid and heat. And we would decarboxylate. So this would be the reaction sequence we would go through to make this compound. And it doesn't matter what two groups are, you put on there, they need to be primary halides, but you put one on, then the other one on, the order doesn't matter because they're primary. They're not really going to get in the way of anything.